Okay, good morning, everyone. Okay, welcome to the calculus class. And since, some student asked, actually, a few students sent me some emails regarding the video recordings and so on. So I posted the previous video recordings on the YouTube. So here is the previous. So let me show you. Um, Okay, so I posted the previous video recordings on the YouTube. So you can, okay, so please check the announcement on the LMS website. So if you visit the LMS, then there will be some announcement regarding the video recordings, and that announcement introduces the link to this playlist. So from the first video lectures on March 4th to up to this March 23rd video recording. Okay, all these recorded videos are uploaded, so you can check those if you want. But as I announced, okay, if if I see a decrease in the number of students participating in the real time this online class, then I will stop uploading these video recordings. So if you attend these online classes, then you can watch the video recordings on, and this video playlist will be updated, okay, on a regular basis. Okay, so please check this, and if you see if you have any problem with these video recordings, please let me know. And then let's go back to our regular class. And okay, so we considered an implicit differentiation. So implicit differentiation considers the differentiation of a function when the function is defined implicitly. So usually you are given some equation in x and y. Okay, so you have an equation in both x and y, so that when one variable, say x varies, then the other variable y must be changed accordingly. So the, in other words, y may be regarded as a function of x in some sense. Okay, and sometimes we can explicitly express y in terms of x, which we consider, okay, but that may not be possible in some situation. So that's why we consider this implicit differentiation. So so yeah, so we consider this example one. So if we have x squared plus y squared equals 25, and if we want to find the dy dx, then what you can do is we can differentiate each side of the equation with respect to x. And then in case of the y variable, when you differentiate y in terms of x, you need to remember that this y is a function. So when y squared is differentiated with respect to x, you need to remember the chain rule, okay? Because that y squared is the composite of a squared function, I mean the power function, and this function y. So if you remember that fact, and then if you perform the chain rule, then you get some expression. And after the differentiation, some term will have dy dx and some don't. Then you need to move all the terms which do not have dy dx to the right hand side. Okay. And then if you do a little bit of cleaning, I mean the rearrangement of the terms, then you will find the expression for dy dx. So let me give some more examples because this is quite useful. Oh, and okay, so let me consider some example. So suppose that I have, say, x squared plus y equals to 0. In that case, when I differentiate the left hand side, then must be the same as the differentiation of the right hand side. Excuse me. Now, when I differentiate x squared with respect to x, so when I consider this left hand side, that is the differentiation of x squared plus the differentiation of y. So when I differentiate x squared with respect to x, you get 2x. And then when you differentiate y with respect to x, you get dy dx by definition. And when I differentiate the right hand side, since the right hand side is just the value 0, that's constant number. When you differentiate this 0 with respect to x, you get 0. So dy dx term has dy dx. As I said, if some term like this 2x does not have dy dx in it, you need to move that term to the opposite side, to the right hand side. So the equation will be negative 2x. Okay, so in this simple problem, dy dx will be negative 2x. So this is an implicit differentiation. Now, in this specific case, in this specific case, I can convert the given equation to some explicit definition of y. In other words, when x squared is moved to the right hand side, we get y equals to negative x squared. So that is this is an explicit representation of y. Okay, so in that case, if I want to find the dy dx, or in other words, y prime, you can just differentiate the right hand side, right? So from this, we can simply get this negative 2x. That is simple. But sometimes you can derive this explicit representation of y, but sometimes that derivation may be challenging. So here is one example. So what if I have, say, x squared and then say sine y equals to 0. So the only difference in this example is that previously I had y, but now I have sine y. Okay, so if we want to derive the explicit representation, well, we can do that. Actually, if you want, sine y is negative x squared, so y will be arcsine of negative x squared. So if you want, you can use this expression and then you can differentiate this y. Okay. We didn't study how to differentiate this inverse function of the trigonometric function yet, right? So at this point, we do not know how to handle the derivative of this y. So the derivation of explicit form of y doesn't help in this at this point, right? So what you can do is we can consider the implicit differentiation. So when I differentiate, so what you can do is we can differentiate both sides of the equation. So we first differentiate the left hand side, and that must be the same as the derivative of the right hand side. And the differentiation of the left hand side is the differentiation of x squared plus differentiation of sine function. Okay. Now, what is the derivative of x squared? We get 2x. And what is the derivative of sine y when I differentiate that function with respect to x? Now, as I said, this y it will be some function of x. So this sine y is the composite of two functions. The outer function is sine, and the inner function is y. So the chain rule says, when I differentiate this composite, we first differentiate the outer function. So if I differentiate sine, you get cosine. So cosine function is obtained. And you evaluate this derivative at the inner function, which is y. And then you need to multiply the derivative of the inner function, which is dy dx. And that will be the derivative of the constant function 0. So we get 0. So 2x does not have dy dx, so I will move this 2x to the opposite side. But the second term has dy dx in it. So, as I said, you keep this cosine y times dy dx on the left hand side, and then you move this 2x to the opposite side, to the right hand side, to become negative 2x. So if I divide this term by cosine y, you get dy dx. So in other words, dy dx will be negative 2x over cosine y. So this is the final answer. That is the derivative of y with respect to x. Just let us consider one more equation. So if I consider, say, x squared plus sine y. Previously, I considered the case when the right hand side is 0. But what if I have x times y? In that case, you need to differentiate both sides, left hand side and right hand side, with respect to x. So if I differentiate the left hand side, that must be the same as the differentiation of the right hand side. So as we did, the differentiation of the left hand side equals the derivative of x squared plus the derivative of sine y. So when I differentiate x squared, you get 2x. And when I differentiate sine y with respect to x, you get cosine y times dy dx. Now, let us look at the differentiation of the right hand side. When I look at the right hand side, I have a product of x and y. And please remember that this y is a function of x. So that means I have a product of two functions in x, and they are multiplied. So I need to apply the product formula, product rule. So that means you need to differentiate one by one. You first differentiate x with respect to x, and then you multiply y unchanged. And then you keep this x as it is, and then you differentiate y with respect to x. So here, let me correct this. So this prime denotes the differentiation of x with respect to x. So the derivative of x is 1. So 1 times y will be y. And then the next term is x times dy dx. Then, as I said, if some term like these two have dy dx, then you collect them on the left hand side. In other words, I want to move this term to the left hand side. And if terms do not have dy dx, then you collect them on the right hand side. So in other words, you move 2x to the right hand side. Then what do I have? Initially, I have cosine y dy dx on the left, and I have new term minus x times dy dx. And on the right, I had y in the beginning, and then this negative 2x came from the left hand side. Now, if I do this, then each term on the left has dy dx. So each term has dy dx. So I can rewrite the left hand side using dy dx as a common term. So on the left, I have dy dx times cosine y minus x. And that will be y minus 2x. So if I divide that equation, if I divide this equation with this cosine y minus x, then we get dy dx. So dy dx will be y minus 2x divided by cosine y minus x. So that will be the derivative of y with respect to x. That will be the instantaneous rate of change of y function with respect to x variable. Okay? So, so if I give you an additional question, so what if when x is, so if I consider point P with 0, not 0, but and yeah, 0 and pi. So when x is 0 and y is pi, the x squared plus the sine y will be 0, and x times y will be also 0. So this p is on the graph of this relation, right? And given this p, if I want to find the tangent line, I need to find the slope and one point. But this one point is given. So all I need is the slope of the tangent line. And dy dx will give you that slope of the tangent line, right? So if I evaluate dy dx at this point, 0 and pi, so when x is 0 and y is pi, your dy dx will be pi minus 2 times 0 over cosine pi minus 0. So you get pi, and cosine pi is negative 1. So negative pi will be the slope of the tangent line. So the tangent line will have the following equation: y minus pi equals to minus pi times x minus 0. Or in other words, y will be minus pi x plus pi. So that will be the tangent line, okay, to the curve at this point P. So in this way, we can find the differentiation, the derivative of y with respect to x when some implicit relation is given. And as I said, given such implicit relation, you don't have to express y in terms of x. Please do not try to express y in terms of x. You can just directly differentiate each side of the equation with respect to x. And then if some term has dy dx in it, you move it to the left hand side. If some terms do not have dy dx, please move them to the right hand side. Then as I showed, then on the left, dy dx will be a common factor. So you can rewrite the left hand side as dy dx times something equals certain expression on the right hand side. And then you divide this equation with this something. Then you get the expression for dy dx. So this implicit differentiation is quite useful when certain equation is given, and especially when from that equation, if it is difficult to derive an explicit relation for y, then you can apply the implicit differentiation. And we will use this implicit differentiation quite often. So please practice this implicit differentiation. Now, okay, so given some implicit relation between x and y, we could find dy dx. Now, if we could get dy dx, the first derivative, then probably there will be a way to get the second derivative or higher derivatives. So, okay, so let us consider this example that might be easier. So suppose that we have some equation like this one, x to the fourth plus y to the fourth will be 16. And suppose that we want to find y double prime, the second derivative of y with respect to x. Okay, given this implicit differentiation, if I differentiate both sides with respect to x, so if I differentiate the left hand side, x to the fourth plus y to the fourth, and that will be the derivative of 16. And from the right hand side, if I differentiate x to the fourth, then you get 4x cubed. When I differentiate y to the fourth with respect to x, then since y is a function of x, okay, so you have some function in x and you are taking the fourth power. So this is the composite of two functions. The inner function is y. The outer function is a power function, x to the fourth. So by using the chain rule, the derivative of that y to the fourth, it will be 4y cubed. That's the derivative of y to the fourth, right? Power function, evaluate this inner function, multiplied by the derivative y prime. And that must be the derivative of 16, which is 0. So from this equation, 4y cubed y prime has y prime, but 4x cubed does not have y prime. So you move that term to the right hand side. So you get 4y cubed y prime will be negative 4x cubed. So if you divide this whole equation with the coefficient of y prime, then y prime will be negative 4x cubed divided by 4y cubed. So after the cancellation of 4, you get the expression for y prime, which is negative x cubed over y cubed. Okay, so that is y prime. Then how can I obtain the second derivative? Well, since this y prime is this, what is the second derivative? That is the derivative of y prime with respect to x. So all you have to do is you can just differentiate this expression negative x cubed or over y cubed. So if I differentiate this function with respect to x, and if you remember that this y is a function of x, so please remember that this y is a function of x. Even though we didn't find the explicit representation, we know that y is a function of x. So, so I have some composite function in the denominator, composite function of x in the denominator, and I have x cubed function in the numerator. So I need to apply the quotient rule when that function is differentiated. So you first differentiate the numerator multiplied by denominator, unchanged it, and then minus numerator x cubed multiplied by the derivative of the denominator, and then you whole thing is divided by the denominator squared. So if I differentiate x cubed, you get 3x squared. Now when I differentiate y cubed with respect to x, then as I said, y is a function. So this y cubed is the composite of two functions, right? U to the cubed. So f of u is u to the cube, and g of x is, say, y. So this y cubed is the composite of these two. So you first differentiate the outer function. F prime of u will be 3u squared. So you put 3u squared evaluated at the inner function y. So 3y squared is the derivative of f prime evaluated at y. You then multiply the derivative of the inner function, which is y prime. So that is the derivative of y cubed with respect to x. So we get 3x squared and 3y squared y prime. And if I consider the denominator, you get y cubed is squared. So we get y to the sixth. Now in this expression, in this expression, y prime is known because, right? Because that's what we get from the previous slide. So y prime was negative x cubed over y cubed. So if I plug in that expression to y prime, then we get this. Okay. So in the second term in the numerator, 3x cubed y squared is multiplied by negative x cubed over y cubed. So we get eventual, okay, so we get negative y to the 6 in the denominator, and the first term is 3x squared y cubed, and then the sign becomes the plus 3x to the 6 and 1 over y. So if I multiply y to the numerator and denominator, this y will cancel with the second y, and then this 3 will be changed to the fourth, right? So in the denominator, you have 7 copies of y. So we get this expression. Or since x squared is common, you can express like this. So this is how we get the second derivative of y with respect to x. If I have the second derivative, you can derive the expression for the third or fourth derivative, right? So let us consider one more example regarding this, okay, before we go to the next slide. So suppose that I have the equation for the circle, say x squared plus y squared is, say, 1. So I have a unit circle centered at 0 with radius 1. Now I want to find dy dx or y prime. So to find dy dx, we already considered this, right? So I need to differentiate this left hand side, and that will be the derivative of the right hand side. When I differentiate the left hand side, I have two terms, so I need to differentiate term by term, right? So if I differentiate the first term, you get 2x. If I differentiate the second term, and if you remember that this y squared is the composite of two functions, then you get, right? So this y squared is the composite of two functions, right? So that is where f of u is u squared and g of x is just y, which we do not know its explicit representation. So to get the derivative of y squared, I need to differentiate the outer function to get, so from this f prime of u will be 2 times of u. So I need to consider 2 times of u evaluated at the inner function g, which is y, multiplied by the derivative of the inner function, which is y prime. So when I differentiate y squared with respect to x, you get 2y y prime, and that will be 0. Now 2x does not have y prime, so I move this guy to the right hand side. So you get 2y y prime equals to negative 2x. Now if I divide this each term with the coefficient of y prime, then y prime will be negative 2x over 2y, which is negative x over y. Given this, if I want to find the second derivative, then I need to differentiate. I need to differentiate this negative x over y, or I need to consider the differentiation of x over y. So please remember that this y is a function of x. So this, for the derivative of this x over y, you need to consider the quotient rule. So you first differentiate the numerator multiplied by denominator minus numerator times the derivative of the denominator divided by the denominator squared. Now x prime is 1, so the first term in the numerator will be just y minus x times y prime. Y prime was negative x over y over y squared. So we get y plus x squared over y squared. Given this expression, if I multiply y to the numerator and denominator, then we get y squared, which is obtained when you multiply y with y. And then when you multiply y to x squared over y, you get x squared. And then we get y cubed in the denominator. So that will be the second derivative of y with respect to x. Okay? So So yeah, this is how we, okay, consider the derivative of, I mean, how we differentiate this y two times. And if you want, you can consider some higher order derivative as well. Anyway, so that is an implicit differentiation. And then let's go to the next section. Okay, now let us consider the derivatives of the logarithmic function and the derivative of inverse trigonometric functions, okay, which I briefly mentioned a moment ago. So let us first consider the derivatives of the logarithmic functions. So, okay, so when I say the logarithmic function, that means this y is defined by something like this. Y is log of x with base b. Okay, now that means x is b to the y. Okay, and given this relation, what do I get if I differentiate both sides with respect to x? I mean, what if I consider the derivative of this guy? Okay. So when I differentiate x with respect to x, you get 1. And please remember that if you differentiate b to the x, you get b to the x times log b, right? That's what you got when I differentiate this exponential function. Now, when you look at this b to the y, I have the composite of two functions, f of u defined by b to the u and g of x, which is y. So when I differentiate the right hand side, I need to apply the chain rule because we have the composite of two functions. And please remember that if f of u is b to the u, then f prime of u will be b to the u times ln b. That was f prime u, right? So let me go back to my original problem. So when I differentiate the left hand side, I got 1 as I wrote down here. And when I differentiate b to the y with respect to x, then I first get the derivative of the outer function, this one, evaluated at the inner function. So we get b to the y ln b. That is the derivative of the outer function evaluated at the inner function. Now that's not the end of the chain rule. You need to multiply the derivative of the inner function. So y prime must be multiplied. So, so to get y prime, I need to divide this equation with the coefficient of y prime. So y prime will be 1 over b to the y times ln b. Now, what is a b to the y? We initiated our consideration with y equals to log of x with base b, and at that point, I temporarily express the x as b to the y, and then I differentiated each side of this equation, and then I applied the implicit differentiation, right? So b to the y was just 1 over x. So this b to the y is just 1 over x. So 1 over x times ln will be y prime when y is given as a logarithmic function. So, so we just have this formula. When I differentiate logarithmic function with base b, you get 1 over x times ln b. That's in the denominator. Okay. So as a special case, when b is e, then ln b will be ln e, which is 1. So that means when I differentiate this natural logarithmic function, you get 1 over x. Okay? So you need to memorize this, or at least you need to write down this formula on your cheat sheet. Okay, so if I want to differentiate log sine x, then this is the composite of two functions, right? You first consider the sine x, and then you consider the outer function, ln function. So if you differentiate this composite, you need to consider, okay, so the derivative of outer function evaluated at evaluated at the inner function, and then you multiply the derivative of the inner function. And outer function is natural logarithmic function. So its derivative was 1 over x. So all you have to do is you need to evaluate this 1 over x at the inner function sine. So this is the derivative of the outer function evaluated at the inner function. If I differentiate sine, you get cosine. So we get 1 over sine over times cosine. In other words, we have cosine over sine, which is just cotangent function. Okay, okay, so we just considered how to differentiate the logarithmic function, and some the calculation of derivatives of complicated functions involving product, quotient, or powers can often be simplified by taking the logarithmic function. And the method used in the next example will be called the logarithmic differentiation. So what is the example? Okay, so here is the example. So we have an explicit, so this is an explicit representation of y is given, but this explicit representation is quite complicated, right? I mean, if you want, you can apply the regular formula to differentiate this. I mean, so if you want, if you want, say if I apply the regular formula, then I have the quotient of two functions. So I have x to the 3/4 times square root of x squared plus 1. So you first differentiate this, multiplied by the denominator minus the original numerator multiplied by the derivative of the denominator over the denominator squared. So if you want, you can perform this, okay, if you want. But, okay, but we can apply, we can consider some different approach. We can consider a different approach other than this. So the idea is this. What if I consider the log of y? Okay, then that will be log of x to the 3/4 times x squared plus 1 over 3x plus 2 to the 5th. Okay. Now, in case of the logarithmic function, what I have is the following formula. In case of log log a times b will be log a plus log b. Log a over b will be log a minus log b. If I have log a to the b, that will be b times log a. So we have those formula. So in this, inside of this parenthesis on the right, I have a quotient of two functions. So that will be the same as log x to the 3/4 times x squared plus 1 minus log 3x plus 2 to the 5th. And the first term is now a product of two functions. So that will be log x to the 3/4 plus log square root of x squared plus 1. And for the third term, I have this power. So I can put this power 5 in front of the logarithmic function. And for the first term, I have 3/4. So that can be located to the front as well. And square root corresponds to 1/2 power. So please remember that x squared plus 1, the square root of x squared plus 1 is 1/2 power of x squared plus 1. So I can rewrite this logarithmic function as ln log x squared plus 1 minus 5 ln 3x plus 2. So that is my ln y. Okay. So this is the expression given. Now I want to differentiate both sides with respect to x. So I want to differentiate both sides with respect to x. Then all you have to remember is that this y is a function of x. Please remember this. Okay? So at this point, you need to remember that this y is a function of x. So when ln y is differentiated, you need to consider the chain rule. So, so if I differentiate, oops, okay, so ln y, what do I get? So when I differentiate ln y with respect to x, then you need to consider the chain rule. So you need to differentiate the outer function, the ln function. That is differentiate to give you 1 over x. All you have to do is you need to replace x with y because you need to evaluate that derivative at the inner function. So 1 over y. But that's not the end of the chain rule. You need to multiply the derivative of the inner function, which is y prime. So that is the derivative of the left hand side. When I differentiate the right hand side, you need to differentiate term by term. When ln x is differentiated, you get 1 over x. When ln x squared plus 1 is differentiated, you get the same result, right? Please remember that when ln y was differentiated, you get 1 over y. The derivative of the outer function evaluated at y multiplied by the derivative of y prime, derivative of y, which is y prime. So when ln x squared plus 1 is differentiated, you get 1 over x squared plus 1 multiplied by the derivative of the inner function, which is the derivative of x squared plus 1, which is 2x, minus 5 times. If I differentiate ln 3x plus 2, you get 1 over 3x plus 2 times the derivative of 3x plus 2, which is 3. So this is what I get when I differentiate each side with respect to x. Now, what I want to find is the derivative of y prime. So in this expression, I want to find y prime only. But on the left hand side, I have y. So I can just multiply y to this whole expression. Then this y on the left will be cancelled, right? So y prime will be y times this part. Okay. So since y was defined by this complicated expression, if you replace y with this expression in x multiplied by this term, that will give you dy dx. So differentiation in this way. So what did I do? I just took the natural logarithmic function on each side of the equation, and then I performed differentiation. Of course, I used some properties of the logarithmic function. Okay. But anyway, that will be simpler than my original initial approach. So here are the steps in logarithmic differentiation. You first take natural logarithmic functions of both sides of the equation, and then you need to apply the basic properties of the logarithmic function to expand the expression. And then you can differentiate implicitly with respect to x. And then you can solve the equation for y prime. And if you happen to have y in the expression, you need to replace that y with the original definition f of x. So that is the formula to use this logarithmic differentiation. Okay? And I will show you some more examples of this logarithmic differentiation in a moment. So And before we consider the derivative of the arcsine or arccosine, let us consider the following expression. So if, suppose that f of x is defined with the natural logarithmic function, then as we observed, f prime is 1 over x, right? F prime of x will be 1 over x. So if I evaluate this f prime at 1, then f prime of 1 will be 1. So f prime of 1, that is 1 when f of x is defined by the natural logarithmic function. That's what we learned, right? Okay, now let us interpret this f prime of 1 using the definition of the derivative. So f prime of 1, that was initially defined by this expression, f of 1 plus h minus f of 1 over h as h goes to 0, right? Now, here h is a dummy variable, so I can replace with h with any variable, say x. So that expression can be written in this form, f of 1 plus x minus f of 1 over x. And then if you let x go to 0, then this expression will converge to the value 1. Okay? So now since f is defined with the natural logarithmic function, f of 1 plus x is just ln 1 plus x, and f of 1 is ln 1. Now ln 1 is 0, right? Right? Please remember ln 1 is 0. So the numerator is ln 1 plus x divided by x, and then if you let x go to 0, that limit will be 1. Now, if you have anything in front of the logarithmic function, you can put this something to the exponent, right? So that is ln 1 plus x to the 1 over x. Now, at this point, please remember that this logarithmic function is continuous. And we have a theorem that if I have a continuous function, then limit of continuous function of x or any gx as x goes to certain value, that will be the same as this continuous function of limit of gx as x approaches 0, right? I mean, we can switch the continuous function and the limit function, right? I mean, these two can be switched. So if I do that, if I apply this one, so I want to apply the limit function first, and then I want to consider the logarithmic function. So if I do that, so if I do this, that will be natural logarithmic function of limit of 1 plus x over 1 over x as x goes to 0. So I have ln something is 1. Okay, then what is this something? This ln means just a logarithmic function with the base e, right? So ln something is 1, then what is the value of this something? This something will be e. So this something will be e. So that was the result we could find from this simple fact, right? We learned, okay, we observed f prime of 1 is 1. And this simple fact gives this formula. The limit of 1 plus x to the 1 over x will be e. You need to observe a few things here. So this x, and this x, okay, these are the same, okay? So 1 plus x to the 1 over x. And as x approaches 0, not infinity, not 1, just 0, x goes to 0. Then this limit exists and the limited value will be e. And please note, please remember that as x approaches 0, this 1 plus x value, what is strange here is that limit of 1 plus x as x approaches 0 is just 1. What is the limit of 1 over x as x approaches 0 plus infinity? So the expression in the base is approaching the value 1, and the exponent is increasing. And at that point, this whole mixture is approaching a constant value, which is slightly greater than 2. Okay, e is 2 point something, right? So the limit exists and the limited value will be 2 point something, which is e. Okay, so this is a very remarkable and useful fact. And sometimes this x, 1 over x, is replaced by n for simplicity, and we get this expression. Okay, if x goes to 0, then 1 over n will go to infinity. So n will go to infinity. So the previous, so that is the same as the limit of 1 plus x over 1 over x as x approaches 0. Okay, so that is the same as this formula 6, and that formula will be quite useful in many fields. So as an example, if I have, say, limit of 1 plus 1 over n to the, say, 2n, and then if I let n go to infinity, then at this point n goes to infinity and I have 1 over n, that is fine, but I have 2n, that is the exponent. So that may be replaced by 1 plus 1 over n to the nth, and then I can consider the second power of this. And as I said, the square function is a continuous function, and in case of a square function, I can switch this continuous function with the limit operator. So that means I can consider the limit of this, and then I can consider its square. And the expression inside the curly braces will have the limit of e. So the limit in this case will be e squared. Okay. And one more thing, I have plus sign here. Okay. So another example, if I have limit of 1 minus 1 over n, and then if I have n here, and then if I let negative n goes to negative n, then when I replace negative n with m, then instead of 1 minus 1 over n, I have 1 plus 1 over m, and n will be negative m, and then the limit considers the case when m goes to infinity, then, as I said, this negative m can be considered as negative 1 power of mth power, and the expression inside the curly braces will have the limit of e, so we get 1 over e as the final answer, final limit, right? So anyway, that's some example of the Formula 6. Now, let us consider the inverse of the trigonometric functions. So, I want to differentiate this function. Okay, I want to differentiate this function. Now, given this, that means this means sine y will be x. That is the meaning of this arcsine. Okay, so if y is defined by arcsine, then so that I have sine y equals to x, then now let us differentiate this new expression with respect to x. And you need to remember that this y is a function of x. Okay. Now, of course, this arcsine, when I consider the arcsine, the function must be one-to-one, so that if I consider the arcsine, the y value must be restricted so that the function becomes one-to-one, right? So when I consider the arcsine, the value of y is bounded between minus half pi and half pi. Now, anyway, given this sine y equals to x, if I differentiate each side with respect to x, then the left-hand side is the composite of two functions. The outer function is a sine, the inner function is y. So by the chain rule, if I differentiate the outer function, you get cosine. So if you evaluate that cosine at the inner function, you get cosine y. That is the outer derivative of the outer function evaluated at the inner function. You multiply that with the derivative of the inner function, which is y prime. And that must be the derivative of the right hand side. So if I differentiate x with respect to 1, you get, with respect to x, you get 1. So dy dx will be 1 over cosine y. Now, cosine, so sine and, but this cosine y is still unknown, right? Because I am given some arcsine of x. Some function in x is given. Now, when I differentiate y with respect to x, I expect something in x. So I'm not happy with this y appearing on the right hand side. So I want to eliminate this y from the right hand side. So what I can do is, okay, cosine y and sine y satisfy this well-known equation. So cosine y squared will be 1 minus sine y squared. Sine y was x, so this is 1 minus x squared. So cosine y squared will be 1 minus x squared. Okay, now that means cosine y will be plus or minus square root of 1 minus x squared, right? So I have two possibilities, plus square root of 1 minus x squared or minus 1 minus x squared. Now at this point, since y is limited between minus half pi and half pi, cosine y cosine, here is the cosine graph between minus half pi and half pi. Between minus half pi and half pi, the cosine function will be positive, non-negative. So on this interval, my cosine must be non-negative. So between these two possible choices of the sign, I must choose the plus sign because cosine is non-negative. So cosine y will be plus square root of 1 minus x squared. So if I plug in this expression to the denominator, then dy dx will be this. In other words, if I differentiate arcsine function, you get 1 over the square root of 1 minus x squared. So that is the result, okay? You need to remember this fact. Now, in case of the arctangent, which is also quite common in our calculus class, as I said, y equals arctangent implies that tangent y is x. So if I differentiate both sides with respect to x, then from the tangent y, there is another composite function, right? So if I differentiate tangent, you get secant squared. You need to evaluate secant squared at the inner function. So you get secant squared of y. That is the derivative of the outer function. You need to multiply the derivative of the inner function, right? That is the chain rule. And that is the derivative of the right hand side, 1. So dy dx is 1 over secant y squared. And as I said, y is given as a function of x. So I expect certain expression in terms of x, not y. So I'm not happy with this secant y squared. So what I can consider is, okay, secant y squared comes from 1 plus tangent y squared, and tangent y was x. So this will be 1 over 1 plus x squared. Now I have some expression in x. And okay, so I'm happy with this one. So that means if I differentiate arctangent, you get 1 over 1 plus x squared. And here are the formula for the derivatives of the inverse trigonometric functions. So previously we considered the derivatives of the trigonometric functions. Now today I'm just introducing the derivatives of the inverse of the trigonometric functions. Of course, when I consider these, you need to be careful with the domain of the variables. So if I consider the derivative of this is the composite of two functions, right? F of u is 1 over u, and the inner function is the arcsine function. So I need to apply the chain rule, right? So you first differentiate the 1 over u function, then you get negative 1 over u squared. So you evaluate this derivative of the outer function at the inner function multiplied by the derivative of the inner function, which is this. And then for this product of two functions, you need to apply the product rule. So given this, you can differentiate one by one. Okay, so please check this, and if you have any questions, let me know. Okay, and please check the YouTube website for the previous video recordings, and if you have any suggestions, please email me. Okay, thank you for listening, and see you next time.
Professor,